Can all of you hear me?
Yes, sir.
So we'll wait for another 2 minutes and then we'll start. Okay, so let's start. Any questions regarding the assignment, the third assignment, office space planning? Yes, no?
No, sir.
And last week I discussed that I'll be traveling on 18th again, the weekend of 18, 19, but then I realized that 18th is a holiday for you, right? Good Friday, Friday.
Yes.
Okay. So then next week is fine, 11th, 12th. Then I'll plan accordingly. So today we'll have lecture 24. Then next week, if I'm there, then Friday, Saturday we'll do 4 lectures again. Then so we'll be done with 28. Then there'll be two more Saturdays in this month. So we'll have 2 online lectures, 29 and 30. So then we'll complete. So next next Friday, Saturday is fine, right? So we can have one class at 2 and another class at 5 as last week on Friday, and then Saturday morning we can have 2 classes. That is okay. Or you have the data science seminar next week.
So no notification about data science seminar.
Sorry.
So there is no notification till now about
Okay.
seminar.
Okay, fine. So then we can assume that there is no seminar. So then
Yeah.
next Saturday, Friday, Saturday I'll be there, and then so next Friday. So then can you guys submit the assignment 3 by let's say by Wednesday night, this coming Wednesday? Then I can go through your assignments on Thursday, and then Friday or Saturday we can discuss. Is that possible? Can you submit by Thursday? Sorry, by Wednesday night? Okay, cool. Then yeah, so then if you are submitting by Wednesday, then we can discuss on Friday, Saturday. Okay, fine. And meanwhile, if you have any question uh, regarding the assignment, you can always drop me an email. So I'll change. I forgot what was the deadline I had put in the assignment, so I'll change that to Wednesday end of day then. Mm. Okay. So today, the topic that we'll cover is constraint programming. 1 minute, let me share my screen. Um, okay, are you guys able to see my screen? Are you able to, sorry, are you able to see the presentation in Chrome?
Yes, sir.
Yeah. Okay. So, yeah, let me move to full screen mode. So, anyone can remind me what was one of the practical applications we had discussed in one of the initial lectures, maybe lecture 3 or 4, something that you can easily relate to of constraint programming, where there is no objective.
One was Sudoku
Yeah.
code, right?
Right. So Sudoku is one example. So in the initial lecture, we had seen how to formulate Sudoku as a mixed integer programming formulation using conventional mathematical programming. So in today's lecture, we will see how to formulate Sudoku in a constraint programming format. So these are some. So this is a very basic overview of the key features of constraint programming. For the problems, to solve the problems that we conventionally do using classical mathematical programming, which we have gone so far in this lecture, any kind of combinatorial optimization problem, we can also do that using constraint programming, and we will discuss about the pros and cons of that in this lecture. So unlike conventional mathematical programming, um, constraint programming is not based on linear algebra. It is based on computer science fundamentals like logic programming and graph theory. And this is particularly important when we work on real world scheduling and sequencing problems, which involves a lot of complex constraints which are very difficult to formulate using conventional mathematical programming. Or even if it is possible to formulate, it will be very, very complex, which will involve a lot of variables. Um, so whenever there is any complex logical or arithmetic relationship between decision variables, activities, and resources, then it's preferable to go for constraint programming. So constraint programming, also called as CP, is can be used as a heuristic to find solutions for MIPs. Um, so how it works is it first tries to reduce the set of possible values of the decision variables that satisfy all the constraints by using logic, graph theory, arithmetic, and other arguments. And then there is some other algorithm which we call as constraint propagation. So we will go through that in the next slides. And also it applies various search strategies until a value is assigned to every decision variable. And the key feature of constraint programming is it may or may not have an objective function. But if there are multiple objectives, then that is something which constraint programming cannot handle. So it should have preferably only one objective. Um, and the major benefit of using CP in scheduling problem is that it does not require enumeration of time. So you had seen in the last week's lecture that we had gone through the job scheduling problem, where you had seen that there are two kinds of formulation. One is the disjunctive formulation, and one is using the time buckets. So you had seen that if the time buckets are high in number, then that will create a lot of variables. But in constraint programming, that is not an issue. So whether it is whether the time is in milliseconds, minutes, or hours, it doesn't matter. Yeah, so as I mentioned, so in CP, we try to focus on finding a feasible solution rather than finding optimal solution. And we focus on constraints and variables instead of objective function. Um, so the goal is simply to narrow down to a very large set of possible solutions to a more manageable subset by adding constraints. The good part of CP is it allows to represent many problems in a way which is very close to natural language description, thanks to semantic constraints. So, for example, if you want to write that I should not have any overlap between two machines at any particular time, at any particular point of time, those constraints are very easy to write using CP. So the benefit of that is you can do fast prototyping. The code is compact. It will not be a very long code, and you don't need to create too many variables, and it's easy to modify. So whenever there is any additional requirement by the user, you do not need to make or think about making a lot of changes in the model. Okay, and in terms of maths, CP does not rely on assumptions about solution space such as convexity or linearity. Anyone can tell me what is convexity in terms of programming, mathematical, in terms of mathematical programming, or yeah, what is the meaning of convexity? Okay, so convexity is basically when we can connect any 2 points in the solution space by a single line. So basically, it means that the solution space is not discontinuous. But in constraint programming, we do not need any kind of assumption like that. So that makes it easy to add a range of constraints, add various complex constraints, such as we can. So till now, we had seen that we cannot write in conventional mathematical programming. We cannot write max, min, and or if I know if then those kind of constraints. We cannot say that if x takes this value, then y equal to 1, else it is 0. We cannot write this kind of constraints. Or we cannot say that z is equal to maximum of x and y, where x and y are both variables. But you can do that in constraint programming. So yeah, that's what the next line says, that you can write nonlinear expressions such as variable multiplications, min, maxes, and absolute values. So this is what a CP tries to solve. We try to solve a constraint satisfaction problem, which is essentially a tuple of variables, domains, and constraints. So variables is something that you already know. Domain is the set of possible or potential values for a particular variable, and C is the set of constraints. So if I have a constraint x plus y equal to z, where x and y are both binaries, uh, then the domain of x and y would be 0 and 1, and we have only a single constraint. So according to this constraint, if you have to satisfy this constraint, then these are the possible values which x, y, and z can take. Right. So out of these, so these will be the feasible solutions, and these will be the infeasible solutions, because x plus y is not equal to z, and second one, x plus y is equal to z, but z is not does not fall in the domain. Okay, so this is in a constraint satisfaction problem, we have we can have any of these options. We can fall into any of these categories. The problem can fall into any of these categories. So we might need all the solutions, that is all the feasible solutions. Only one solution, which could be either a feasible solution where the user does not have any preference, or user might need a reasonably good feasible solution, or if an objective function is provided, then the optimal solution. Or we can determine if a solution exists at all or not. So what is the solution of a constraint satisfaction problem? We will have a state where state is assignment of values to some or all variables. So we can say that the assignment is complete when every variable has an assigned value. Assignment is partial when one or more variables have no assigned value, and consistent assignment when is an assignment that does not violate any constraint. So we can say that a solution, we have obtained the solution of a CSV when the assignment is complete as well as consistent. That is, all the variables are assigned and we are not violating any constraint. So these can be the different types of constraints based on the number of variables we are using. So we can have only one variable. So this screenshot is an example of is a screenshot of the formulation of graph coloring problem. So the first example, the first constraint is a unary constraint where we have only one variable. In the second constraint, we have two variables, and then we can have more variables, or we can have some soft constraints. So soft constraint is when we combine optimization with CSPs. That is we would say that whichever constraint results in least violation, we are okay. I mean, in a scenario where it is not possible to satisfy all the constraints simultaneously, we will try to violate the constraint which would require least violation. So these are some of the types of variables that we can have in a constraint programming model. We can have discrete integer values, or we can have uh, expressions, and or we can have constraints. So if you see at the list of constraints, apart from equal to, greater than equal to, less than equal to, you have already seen. But apart from that, you can have strictly less than or strictly greater than. You can have not equal to. You can have and. Yeah. You can have and or implies those kind of logical rules, or you can have different constraints like all different, or all different means if I have 10 variables, let's say x1 to x10. If I say all different, that means none of these variables would have a value equal to any of the other ones. And we'll go through the other ones later. So these are different. These are some of the special constraints and it's not just this. It's not that we have only these 6 special constraints. There are many more. So these are constraints which you can write in constraint programming, which makes the job of the model or the modeler. I mean, I will not say model, but job of the modeler much easier. Okay. So apart from that, you can have interval variables. So interval, I think we'll do this later. You can have different kinds of scheduling rules. Scheduling rules in terms of how many jobs can be performed at a particular time. So you can have disjunctive schedule, which means each resource can perform at most one activity at a time, or cumulative schedule when each resource can run several activities in parallel as long as the resource capacity is not exceeded. Uh, Sorry, there was a power cut at my side. Um, Let me share my screen again. Um, are you able to see the PowerPoint?
Yes, sir.
Okay. Okay, so these are the different kinds of scheduling rules. So again, these are certain rules you might have in a manufacturing setup or in, let's say, in an airline. I mean, in an airport where you have some restriction on the number of. So there the resources will be the number of will be the gates, and so on. Okay, so these are some of the rules, some of the special constraints that you can have in that that constraint programming model can solve. So you can have precedence constraints. Precedence constraints means, so you have seen in the last lecture, job shop scheduling, that you can have, there will be some rules around which job needs to happen before, let's say job X needs to happen before job Y. So that is very easy to formulate using CP. You can have some optional tasks. You can have activities which are parallel with common resource, or you can have some rules around time windows. For example, some tasks cannot start or end at a particular time, or they cannot overlap, or there needs to be at least this much break between two activities, between two jobs on a machine. So those kind of um, problems, it is very easy to formulate in CP. And then in terms of resource constraints, we can have different, you can formulate different scenarios, like a warehouse in the logistics application must be in the same region and stock the product. The crew must include nurse or an emergency medical technician. So this is, and the first one was, and the second one is or. The next one is not, that is total cost must not exceed budget, or if then, that is if inventory is below threshold, then reorder. So these are certain things which we can formulate using CP. And compatibility and incompatibility constraints is, let's say if X is 1, then Y has to be 1, so that is compatible, or if X is 1, then Y has to be 0, that is incompatible. So those kinds of rules you can easily model. Apart from that, so precedence constraints is something which I was just discussing. So you can have different kinds of precedence. So if you have two jobs A and B, and there can be a delay, may or may not be a delay between jobs A and B, then you can have all these different scenarios based on whether there should be a delay or whether there should not be a delay. And with respect to start and end time of A and B, there can be these different scenarios. Apart from that, you can have, so specialized constraint, I mean, you can have all different constraints. So this is something which I just told, that if you have different variables, then you can have a rule that all of these variables will take different values. And uh, on top of that, if you have this minimum distance constraint, it means that if the minimum distance is, let's say, 2, then the delta between any two variables has to be at least 2. So you cannot have 1 and 2 as two values. You have to have 1 and 4. Okay. So apart from that, you can have packing constraint, distribution constraint. I'll skip this. Also, you can have lexicographic constraint, which means that if you have two different arrays, and then if you have yes, no. Are you guys there?
Yes. Also,
Yeah, can you repeat the question once?
Yeah, sorry, there was a power cut again. Okay. No, that was not a question. So this was I was what I was explaining. Um, so this is lexicographic constraint. That means if I have two groups of expressions containing the same number of values, then if they are in order, then I mean if A, B, C are in increasing order and D, E, F are in increasing order, then this constraint will if it's a lexicographic constraint, it means that either the A will be less than D, or A will be equal or if A is equal to 2, then B, then D, then B has to be less than E, and so on. Okay, now what is the difference? Now, let me, before I go there, let me go to some examples of CP application. So this is how you can formulate a CP using, I'm sorry, you can formulate a Sudoku problem using CP. So just go through this for a minute and let me know if this sounds, if you understand this. So this is something very straightforward, but if you have any questions, you can ask. So here I and j will range from 1 to 9. So any questions around this constraint? So do you understand all the constraints? Okay. Any questions around this? Anyone can tell me what is the third constraint? This one?
so in every block, all the numbers are different.
Yeah. So this all different is CP syntax. I mean, is it not syntax, a modeling construct. So using that, you can easily model this. Now, last lecture you had seen the job shop scheduling, right? So, uh, so using MIP, and again, you can go through this formulation. First, you can go through the MIP formulation. So this is similar to what and we have these constraints. So constraints are not formulated, but because we had already gone through that. But this is the variable construct, and this is the objective function. So we need to minimize the make span, that is the total time taken by all the jobs, and we need to ensure we need to adhere to the precedence constraints between the operations, the machine capacity, and we need to link the variables xijt with ci. Right, and if now you can go through this CP formulation and let me know if you have any questions. Okay. Any questions?
This I is machine, right? I variable
No, I is job. Yeah, I is, you can say, kind of machine. Yes.
and J is job.
Yes.
Okay.
Yeah. So basically, this constraint, no overlap, says that once you start, so start is the starting time, and the duration is the duration, the time for which the job will last. So once you start on a machine, there will be no overlap with another job, right? And precedence is, we can start the j plus one job only if once the jth job is completed. And you're trying to here you're saying that we are trying to minimize the max. That means minimizing, you're trying to find what is the last operation, and you are trying to minimize the time by which that gets over, right? So anyone can tell me which is faster, MIP or CP? So in general, CP is faster because of the because for large problems, MIP will have a lot of variables. But the point is, in this case, you have only one objective. So if you have multiple objectives, then CP, apart from minimizing make span, if you have a lot of other objectives, like let's say you want to minimize number of machines, number of changeovers, blah blah blah, then maybe CP will not perform as good. That time, in that case scenario, MIP is better. But if you have only one job, then sorry, one objective, then it's better to go for CP. Okay, so now let's look at another problem. This is again a kind of variant of the earlier problem. So we have certain what do you call, tasks, and we have resources to do these tasks, and these tasks take, and these resources have a certain capacity, and these tasks have a certain processing time. So in this picture, what you see is a1, A2, A3. These are different tasks, and the length of the width of the box represents the duration of the task. And you can see these different arrows. So these arrows indicate the precedence rules. That means A1, after A1 you can do either A3 or A2, and after A3 you can do A6 and A7 and so on. So how do you formulate this using constraint programming is the question. And also you need to adhere to the resource constraint. So the resources are marked as with the the green and red bar, and the height of these bars represent how much capacity of R1 and R2 is required for each activity. So you need to uh, assign every task with the resource, and you need to find when a task starts on a resource, and what time it ends. That will be determined by processing time. So the objective would be to minimize the schedule make span, that is the latest time. That is, you want to minimize the time by which you complete all the tasks. So again, I'll give you a minute so you can look at the MIP formulation, and let me know if you have any questions.
Sir, one more thing. We are supposed to submit by Wednesday, right?
Hmm.
Yeah, okay.
Yeah, yeah, Wednesday, yeah. Wednesday,
Wednesday,
end of day.
end of it.
Yeah,
Okay.
yeah, end of day. Yeah, so you can go through this formulation, the MIP formulation. It is pretty similar to the formulations that you have seen earlier, but you can still go through. So, if you have any question regarding any of the notations, you can ask me. Okay. Any questions on the formulation? Do you understand this? So, what does the first constraint do? Anyone? Okay. So the first constraint will tells that one job can be assigned at one time, and the second job says that this job must be completed before the next job, and the third constraint is says that the capacity, we should not exceed the capacity of the resource. But I actually picked this up from internet yesterday, but I'm not sure why we have so many sets: A, P, R, H. I think R is resource, A is activities probably, P is the precedence, and what is H? I don't know. Anyways, and so this formulation, this can be also formulated using CP in this way. So we need to minimize the max of end of AI, and so this is the special constraint here, this is the end before start. So this is something which is very special to CP. So this makes our, so by using this, you can avoid all the precedence constraints and all. So this will ensure that you start the next job only after the previous job has ended, right? And this is the um, usual capacity consumption constraint. So we are saying that, so usage is defined in this constraint, in this line. So we are saying that the total consumption, resource consumption of a job is equal to is equal to usage. So, and sorry, total resource consumption is equal to usage of this resource, and this usage of the resource cannot exceed the capacity of the resource, right? Okay, now
Sir, what is a conical bracket say in the last line? Yeah,
A,
what is that?
again, I'm not sure about the syntax, but I think it means that AI and AJ
You,
are consecutive tasks.
oh, okay.
And also
And
I'm
what
sure
what
this.
language is this? Like,
Sorry.
what language is this?
This is probably C. I don't know that, but I think this is C. But
Oh,
I just got this from internet yesterday, and I was tempted to put this. But you can understand the overall theme, right? So we are using this
yeah.
end before start, end of. So these are the most important things. So this end of and end before start. These are properties of the CP solver, right? And the rest of the things, this is specific to the language, whether you're using C, Python, Java, it will differ. But this end of and end before start, these are specific to constraint programming solver. Yeah. So I think one slide I haven't put here, that uh, some of the common, so all the optimization solvers that we discussed. Can you name, each of you name one of each, name an optimization solver just for
And
revision?
Gurobi.
Yeah. What else? What is the best? Okay. What is the rank? I mean, there is an official rank as such, but yeah, I mean, unofficially, what is the rank of Groby?
It's second, I guess.
Yeah. And what is the first?
I forgot the name. I mean, it's a paid software. Yes,
Yeah. Yeah, no, what about Groby? Is it paid or unpaid?
yes, sir, it's paid.
Yeah, Groby is paid. So Groby has actually their price has increased drastically in the last whatever few years. I don't know how many years, but because the popularity has increased, and the most popular solver is in number one is Cplex. So Cplex, I mean, it's the full name is IBM iLog Cplex. So Cplex is owned by IBM. So that is number one, and then Groby is number two. Again, these are not, there is no official ranking as such, but generally this is unofficial ranking. So yeah, so the point what I was stating is, so I think Groby does not have any constraint programming interface. So what I mean is, if you have um, if a solver has you can solve MIP through a solver, does not necessarily mean that you can also solve CP through the same solver. So all solvers do not have a CP feature. So Cplex Gurobi, I don't think it has. Cplex has something called, I forgot the name. So I mean, it has a platform where you can solve constraint programming. And so apart from that, there is another solver called FICO Express. So Express is owned by FICO. So they also have their own platform called Calis, which can solve CP problems. And apart from that, Google OR tools also can solve constraint programming problems. So in my previous company, we used to solve a lot of so we are using FICO for mixed integer programming problems, but we are using Google OR tools for constraint programming problems. Okay. Okay. So now let's look at this problem statement. So so this is, so here we are, what we are trying to do is, and this is a problem we are trying to solve in my previous company. So uh, first did I explain to you what is changeover earlier? Anyone, if so, can anyone tell me what is changeover? So basically, on sometimes in factories, on a certain machine, if you cannot,
Machines are
uh,
rotated. Yes.
no, not exactly. No, let's say on a particular machine. Let me give you a simpler example. From Okay, first let me tell you what is changeover. So let's say on a machine, if you're performing job X after job, sorry, you're performing job Y after job X, then you cannot start, if there is a changeover, that means you cannot start job Y immediately after job X. You need a certain time. It might be 20 minutes, it might be 1 hour, it might be one day uh, to change the machine configuration so that it can move from machine job X to job Y, because there might be some leftover parts of the job X which needs to be cleaned, or sometimes, so these days most of the in most manufacturing companies, machines are very highly automated, so you might need to change some internal configurations that it can change to switch over to job Y. So that time is called changeover time, and obviously the number of changeovers, I mean, especially it depends. Like as I said, it can be 10 minutes, it can be 20 minutes, it can be 1 hour, it can be like one day. So it obviously you should have lesser changeovers, because if you have too many changeovers, that will reduce the actual time the machine is on. And sometimes what happens is not necessarily that for all combinations of jobs you need to have a changeover. So let's say for job X to job Y you need a changeover, but for job X to job Z you don't need a changeover for that machine. So for that machine it is better to produce. It is better to have production of job X followed by job Z instead of job Y, because then you are saving the time, saving the changeover time, right? So that's essentially what is changeover. So okay, now coming back to the simple daily life example, not a very relevant one, but still it's a good one, I think. So let's say if you are cooking let's say paneer butter masala, and after that you're preparing chicken curry, then you don't need to clean your utensils. You can probably use the same utensil, but after your curry, if you're trying to prepare some sweet dish, you obviously need to clean it, right? So that you can think of as changeover. Okay, so now in this example, in this slide, the problem is there are certain machines, and on these machines you need to produce you need to produce different products. And just think of that as the jobs. And so let's say if you have 100 products, and for if you are producing product 2 after product 1 on a certain machine, then you need a changeover. But if you're producing product 3 after product 1 on a certain machine, on that same machine, you don't need a changeover, right? And these products have different demand on a particular day. And now the objective is, how do you objective is to schedule the different products on different machines, so that you are maximizing your demand, maximizing the demand satisfaction. That is, you're producing as much as possible, and you are minimizing the number of changeovers. So what you see on the picture that you see here, this is a tentative, this is an indicative output. So the red bars represent the changeover time, and the different blue, yellow, and green, these are the productions. These indicate the production that is happening. And sometimes you see a red right at the beginning of the day. That means that the earlier day there was some production, and that we have to perform changeover before on that machine before we switch to the current day's production, right? So this is the this is the output what you need. And so these are the objectives that you need to maximize your demand satisfaction. Satisfaction, you need to minimize changeovers, you need to minimize number of machines used. But obviously this is lower priority than meeting the demand. So that means if you have lesser if you have less demand on a particular day, then you don't need to run all the machines. You can run only, let's say, 80% of the machines, and maximize the number of items for which we are fully meeting demand. So what this means is, let's say if I have a product in which my demand is 10, and I have another product in which my demand is 100, and my capacity is 10. So one is, we had already gone through the fair share allocation earlier, so you try to do a fair share allocation between these two products. But what we try to do here is, if the demands are very very different, in this case it's 10 and 100, then instead of trying to proportionately balancing, you should try to fulfill the demand of the product which is less in number. So in this case, you fulfill the demand of the product having only 10 demand, right? And then out of these 100 products, there are some products which are higher priority, some which are lower priority. So these are the objectives, and the constraint is that how much time you have in a shift. That means you have only 12 hours in a shift. how many changeovers you can perform on a machine. So you can see in this picture that every machine has only one box, so only one changeover, and the maximum changeovers across all machines, and the maximum changeovers that can happen parallelly across all machines at a particular point of time. So that means if you see at the beginning of the day, you have there are three changeovers happening parallelly, so there can be some limit on this number. The ratio of the demand of an item to number of machines on which the item is produced. That means if the demand of so this simply means that if a product has very high demand, then you will not try to produce the entire product on only one machine. You will try to diversify across multiple machines. And this one is, if a machine works on an item, it should be for at least X minutes. So you cannot run a product on a machine for only 3 minutes. It should be for at least, let's say, at least 30 minutes. And this one we already discussed, that only some pair of consecutive products require. So items actually means changeover here. Sorry, items means products here. So not all pairs of consecutive products require changeover, only certain pairs require. So output would be when a machine should start and stop working on an item. Now, one point to mention here is that you can have a product split across multiple machines. So you can produce 40% of the day's demand from one machine, and 50% from another machine, and 10% from a third machine. That is allowed. Now, can anyone tell me which of these constraints is most difficult to model using mixed integer programming? Anyone? Are you there? Are you guys there? Yes, no? Hello?
Yes, sir. We are here.
Okay. So yeah, so out of these, probably this is a bit complex. So out of these constraints, this one, the maximum changeover that can happen parallelly across all machines, this is very difficult to formulate using mixed integer programming, but using constraint programming, it is much easier. So I think we had discussed about in today about the overlap constraint. So using overlap constraint, you can model this using CP. So you can say that. So let's say the rule is that at any point of time you cannot have more than three machines undergoing changeover. Then you can say that you can write that overlap less than equal to 3, right? And the reason why we have this kind of a rule is because in this case, the changeover requires human intervention, and they do not have more than three people at any point of time. So that is why they cannot allow more than three changeovers to happen at any point of time. So in this particular project, what had happened is we had initially formed. So this requirement was not there from the business initially. So we had formulated the rest of the problem as a mixed integer programming problem, and then once after we built the model and we showed the output to them, they saw some instances where there were more than three changeovers happening parallelly, and then they said that this cannot happen, this is not acceptable. So we can have maximum three changeovers at any point of time. So then we had to completely scrap the mixed integer programming model, and we had to change to a CP model. And I mean, using mixed integer programming also you can do this, but it would be very, very complex, and it would be very time consuming and um, difficult to do. So that's why we switched to a CP model only for the sake of this constraint. Okay, now the question that you may ask is, I earlier mentioned that CP works better when you have only one objective, but in this case we have 4 5 objectives, right? So now in this case, what we did is we kept in the CP formulation, we kept only the first one, the first objective, and the remaining objectives we removed. I mean, we either moved to constraint or we moved to pre-processing. So this one we moved to pre-processing so that we are giving we are trying to find some coefficients that we are able to give, I mean, penalties that we are able to find, prioritize. We are able to give preference to higher priority items, and the others we move to constraints. Okay. So now let's look at the solver log of CP problem. So this is the problem characteristic. So we have around 3000 variables, around 853 constraints. The time limit is 30 seconds. So this is the memory usage. And so this is essentially the solver log, the path the solver takes, and it takes around 1.37 seconds using around 55 MB memory. It explores, so these are the branches it explores, around 35,000 branches. And this is the final information with the solution status. So it found six solutions, that is six feasible solutions. Out of that, the best one had an objective function of 826. So number of fails, meaning the number of nodes it tried to explore, but it didn't find it a feasible solution. And the total time spent in solve was 30 seconds. So basically, so here it says search terminated by limit. That means it stopped at 30 seconds because we had put a limit of 30 seconds. Yeah, so this is what the solver log looks like. Now let's look at some successful applications of CP in the industry. So, so I think you already solved a problem earlier on sports scheduling. So this is a similar problem. So for a 8-team round robin timetable, um, they had to schedule. I mean, they had to find the optimal, or rather the feasible schedule. So using conventional, and this was done way back in late 90s. So using conventional mathematical programming, it took around 24 hours, while using constraint programming, it was solved in less than a minute. And this is the schedule that it came up with after solving this problem. And the second application is gate allocation at Hong Kong airport. So you've already seen how why gate allocation is important problem. And so this was around in 2007, when there were around 800 flights in a day, and the problem was to schedule these 800 flights for the approx 5 million passengers. And using constraint programming technology in iLog Cplex, they were able to implement this model in 4 months. Okay, the next application is in the port of Singapore, transshipment. The transshipment is basically when you have shipments coming in from different parts of the world, and you are reassigning to the to the destination location. So this port connected to 600 ports in 123 countries via 200 shipping lines. And the problem was to assign yard locations under various operational and safety requirements. So this was also solved using constraint programming. The fourth problem is, sorry. Yeah, railroad optimization. So Netherlands railways had around 5.5K trains per day. And using constraint programming, they were able to, so the problem is essentially how to schedule the different trains so that you are able to meet the demand, and you do not have you are doing a fair share across the different cities, and you are staying within your train capacity constraint and so on. So using CP, they are able to do this, and this gave them an additional profit of $75 million annually. So okay, so now let's go back to some earlier points I had skipped. So these are yeah, so these are some of the comparisons of CP and some of the differences between CP and IP. So the main thing which we need to look at is what are the pros and cons of CP versus IP. So CP, as we discussed, addresses problems which are potentially non-convex or too irregular, non-linear. Um, and the drawback of this is it cannot find a solution gap, so it cannot it cannot compute relaxed solutions of a problem, and does not have gap information between the best found solution and the theoretical bound which MIP can provide. While on the other hand, CP is more computationally intensive because it will store a decision. It will require much more memory because it stores domain information in the variable. However, what happens is the formulation in CP is itself much more compact. Hence, it's not necessary that a big CP problem will essentially take more time than than an MIP problem. Now, in terms of functionality difference, so sequencing and scheduling is obviously much better works much better using CP. Messy constraints, that is constraints like you saw earlier, the overlap constraints, those constraints are definitely much easier to formulate using CP. The model is much more succinct and precise and compact. The constraints, it's convey the problem structure, which what that means is just by reading the model, a layman can also tell what is the problem that we are trying to solve, while in MIP you need a mathematical expert to explain or understand the interpretation of the different constraints. In terms of ability to handle very large number of variables, again, CP is not very good in that. I mean, they are kind of CP and IP are kind of equivalent. CP, one issue of CP is not there are not too many state softwares or solvers which can solve CP problems, unlike IP. And solution gap, as we mentioned, is not available in CP, but it's available in IP. In coming to the algorithms which are used in CP, I think all of you would have read about large neighborhood search in computer science. So I've not covered that. But apart from that, there are some other logics which it uses. So one is backtracking search. So backtracking search is what it does is, if you see this example, it tries to color every state at the single color at every step. So in this case, it is trying to assign the first step. It is trying to assign a color to the western state. So it first tries with red color. So basically, for every possible value, it will do a depth first search. That is, it will try to evaluate all the combinations, and if it is unsuccessful, it will come back to the starting point. So it tries with red color, and then it sees that, and then it tries to assign a color to the next state, and it sees that this color is infeasible, but this green color is feasible. But so then it will try to, once it finds a feasible color, it will try to explore further. So again, for the southern state, it will try to assign three different colors and see which one. So in this case, it tries to find it sees that assigning red or green color to the southern state is infeasible, so it will assign the blue color. And then, since blue is feasible, it will again it will go ahead with this combination and try to uh, explore what happens with the other states colors, right? Now it will come back to all these this shaded or this unexplored options only if the other options in the other branches have not yielded a feasible result. Only then it will come back. So that's why it is called backtracking. So only when it finds infeasibility, it will come back and go explore the next node, right? um, so the drawback of this algorithm is that it doesn't it is an uninformed algorithm. So that means it does not know about the probability of succeeding on a particular node. So in general, it's not that it doesn't have that good performance. And the other algorithm which CP applies is what we call as constraint propagation. So that means for every variable, to it will try to reduce the domain, and once it is able to reduce the domain, that is reduce the set of possible values, it will communicate this information to all the other constraints, so that all the other constraints can in turn reduce the possible values, and this cycle repeats or continues until we find a feasible solution, or that we conclude that the model does not have any solution. That means either a failure occurs or we get a feasible solution. So this is an example of how that happens. So I'll not go through this, but yeah, you can read this example. um, so apart from that, it applies some heuristics. So these are again very uh, easy to understand heuristics. So one is what we call as minimum remaining value. So it will choose the variable with the smallest remaining domain to assign next. So that means, let's say if I have 10 variables, and these 10 variables have different range of possible values. So it will try to first work on the variable which has the least possible value. So let's say it will work on a variable which is binary. So it can take only two possible values. So it will try to fix that variable. Then it will move to another variable which has next lowest possible number of values, and it will try to fix that variable. So in this way, it's able to narrow down the search space more efficiently by minimizing the number of remaining possibilities at each stage of the search process. So uh, it focuses on variables that offer the highest potential for progress. So basically, it is trying to focus on the most constrained parts of the problem. So this leads to earlier failure detection or solution finding. That means that you can very quickly find whether the problem is infeasible because of a particular variable, or you can proceed further. The next heuristics that it applies is what we call as least constraining value. That means it chooses the value that rules out the fewest options for connected variables. This helps to maintain flexibility in the search and reduces the need for backtracking. Degree heuristic is assigning a value to the variable that is involved in the largest number of constraints on other unassigned variables. So if let's say a variable is present in 1,000 constraints and another variable is present in 800 constraints, it will and we have not found the values for the variables in any of these constraints, present in any of these constraints, we try to focus first on the value which is on the variable which is present in 1,000 constraints, because that will have more impact. So once we find the value with I mean once we solve for that variable's value, then we try to propagate that value to the other constraints. I think that's more or less what we wanted to cover today. So, any questions, students? Okay, so I'll share this this lecture slides, and then you can go through the slides, especially the algorithm part. Some of these constraints are very important. So they are used in a lot of other areas also, in graph theory and in computer science. So you might see some commonality. Okay. Any questions? Okay, then if no questions, then we'll stop here. And next lecture will, next Friday, Saturday, we'll try to, I'll be there in FCMI, and we'll try to cover some other topics, including the evaluation of your or discussion of your assignment submission. Yeah, and one point, so when you're submitting your assignments, please rename your file so that it has your name, and preferably at the top of the assignment, you can just write your name. That would be helpful. Yeah. And try to ensure that whatever mistakes were discussed in the earlier assignments, so we're not repeating those mistakes. So you're specifically mentioning what the variable does, what the constraint does, and you do not formulate as something as a nonlinear in a nonlinear way. So I think this assignment is anyways a bit easier than the earlier two. So let's see. Okay, any questions? Yes, no?
No, sir.
Okay, fine. Then we'll meet on Friday. And if there is any data science seminar or anything coming up, let me know. So we can change the timing. I'll change the timing accordingly on Friday. Yeah.
Okay, sir.
Okay. Thanks. Thanks, guys.
Thank you.
Thank you.